Okay, we continue with our linear functions examples. This time we have the spring deflection example. And so as we read there, a force is applied to a preloaded spring along the length of the spring, causing it to be displaced. The relationship between the preload force measured in newtons and the applied force and the displacement measured in meters of the spring is F of D is K times D plus F0, where F of D denotes the force that must be applied to the spring to achieve a displacement of D. F of 0 denotes the preloaded force, and K is a parameter known as the spring constant measured in newtons per meter. And then it tells us at a force of 1 newton, the spring is displaced by 100 millimeters, and at a force of 5 newtons, the spring is displaced at 9 millimeters, and then asks us a series of questions. So let's set that up and work through those. Okay, so we can see over here on our engineering paper, we've set up basic design. You can here see a somewhat poor drawing of what's going on in here. We have a spring attached somewhere. We apply a force to it along the length of the spring, and that force causes some sort of displacement. They've given us the relationship that defines that. They've given us a few values that for a force of 1 newton, it's 100 meters. For a force of 5 newtons, it's 900 millimeters. And then the required, and so we'll just go through this step by step. You'll see, of course, I wrote them in much shorter language here. On the right side. The first one, just again, we wanted to find which one are the independent, the dependent variables, and so on. All right, so we have 4 things we want to define, and we have 4 variables that are going to match up to that. So the independent variable and the dependent variable. So of course we can look at our function, and we see that f of d is k times d plus f0. So f of d tells us that f must be the dependent variable, and that's measured in newtons. F, which is our applied force in newtons, is our dependent variable because it depends on our independent, which is d. So we have our independent or dependent variable. Then the slope, so if we have a linear function, the slope is the value that is multiplied by our dependent variable. So here we see that k is multiplied by, so there we see slope is k, our spring constant, which is newton per meter. And they told us in the problem that the units were newtons per meter, but if we didn't know that, because they told us that in the problem, we could figure out the units on k by knowing that it's going to get multiplied by meters, and it has to come out to be a unit of force of a newton. So when we multiply k times d, we have to get newtons, so it must be newton per meter, which only leaves us one left, but also we know that it's the one that looks like it's out there on its own. So it is f0. So there's f0, which is our preloaded force in newtons. And again, until we get comfortable with this, you might always flash back to what we remember in algebra, y equals mx plus b. So this is y, m times x plus b. So that helps us keep everything straight. Part B asks us to determine the value of the spring constant and the preloaded force. So on part B, we want to find k, which we know is the slope. So the way we find slope is the difference in dependent values divided by the difference in independent values. So the difference in f's over the difference in d. And if we use the points as they're written out, remember we've got 5 newtons minus 1 newton over 900 millimeters minus 100 millimeters. And so we would end up with 4 newtons over 800 millimeters. I could go ahead and do that and then convert it at the end, or another way to think of that is to convert these values first and then work it out. So let's just go ahead and continue down the path we're on. So I get that it's 0.005 newtons per millimeter, but remember I want my constant k to be in newtons per meter, so I would need a conversion factor. So to convert it, I would multiply by 1,000 millimeters divided by 1 meter. My millimeters would cancel out, so I would be left with newtons per meter, and I get a value of 5.00 because I had 3 significant figures for this answer, because it's a mix of subtraction with division. So 3 significant figures gives me 5.00 newtons per meter. I could have gone the other route, which would be to convert the values up front, and I could have gotten D in terms of meters early on instead of millimeters, and so known that 1 meter divided by 1,000 millimeters, so my millimeters would cancel. I'll do that in pencil so as to not mess up the problem. I would do the 0.100 meters for the first displacement and 0.900 meters for the second displacement, and then I could use those down here. So if you see the way I worked it out in blue, 5 minus 1 over 0.9 minus 0.1 gets you 4 divided by 0.8, which gets you, again, 5 newtons per meter when you put it in proper units. All right, so the second part of B asked me to find what is the preloaded force. So again, I would want to use, I know that the function, I've got a slope in here now, I still need to find the intercept. So I can use either point, will work in there. And one of the key things is making sure I keep the unit straight. So I'm going to use the first point and plug those values in. And so I know that 1 Newton has to equal 5. And it helps if I remember what this is. Remember, it's 5 newtons per meter is my spring constant times D. And my D, so if I want that to work out, I better use what it is in meters. So my D is 0.100 meters plus F0. So again, I can subtract that out and solve for F0. And I get that F0 is 0.500 newtons. Again, make sure I've used the right numbers for the figures, which is 3 is good, and that I have used units, which is newtons. And again, just to show you, different minds think different ways. I also could have solved this equation for F0 first and got that F0 was F minus K times D, and then plug in the values of 1 Newton. The value of K is 5 newtons per meter, and that I have a displacement of 0.1 meters, and I get to the same result. Again, determine whichever one works for you, but you do want to take advantage. You always want to make sure that you're showing enough equations and then plugging in values to be able to solve something correctly. Oftentimes students get in the habit of just throwing numbers on a page, and it's hard to remember what those are. That's why we always write the equation and then plug in values. And so now that we've got the value of our constant and the value of our intercept, our constant slope and our intercept, we can rewrite this equation as f of d is 5 times d plus 0.5. Not something the S is to express yet, but it's certainly something we need for the rest of this problem. Okay, so we start setting up on our next page for part C. It wants us to actually it wants us to express displacement as a function of the applied force. So what we have from our function is the applied force as a function of displacement. What it's asking for is what we call the inverse function. So we want d as a function of f. What is that? So how do we do that? Well, we do that by solving for d in terms of f. So we start with our equation. Notice we'll ignore calling f a function as a function of d now. We'll just use it as a variable because we're manipulating it, actually working to get to the other side, so it makes sense to do that. And then we would just work through some algebraic steps to get. And so if we solve for d, we subtract 0.5 from both sides, we divide both sides by 5, we get this expression. But generally, if we're wanting to write d as a function of f, we want to put it in the same linear form that looks like a linear function in terms of slope-intercept form. So while this is technically true, we want to go one step further. So to put it in slope-intercept form, we go ahead and divide each part by 5, and so we see we get this coefficient of 1 over 5 times f, so there's our slope, and we get a value of 0.500 divided by 5, that's our intercept. Or if we were trying to answer it into MyLabs or something like that, or some other sort of grading, it usually makes sense to write the slope since we've done this with the previous, we wrote the slopes as decimals, not fractions. So our slope as a decimal would be 0.200, and our intercept would be 0.100. And again, notice, of course, that the units on these would be different. Since D is measured in meters, this must also have units of meters. And since force is measured in newtons, this constant must have units of meters per newton, which makes sense, again, if you remember where these came from, being that this 5.0 is newtons per meter, so when we divide it, it flips its value to meters per newton. Because, of course, this is measured in newtons, and this is measured in meters. So all those things might work out. And again, for the sake of different thoughts, you might have solved it out and then plugged in values. So if you did that, again, you could start from the original expression, ignoring that f is a function of d anymore. Subtract f0, divide by k, simplify in terms of dividing each term by k. So you get that the slope is 1 over k, which is the same thing we see here, and that the intercept is negative, the intercept in the other direction divided by k, which turns out numerically to be the same over there. And so the more and more, if you start to do it more and more by variables, you'll see oftentimes as we do the inverse, what you get to flip the variables is you get 1 over the slope and you get negative whatever the intercept is over the slope is a repeating thing. Or another way of saying that is that x usually equals 1 over m times y minus b over m is a recurring theme for inverses. And you can work that out and see exactly that that works every time. One of the key things for inverse functions is you could take this expression, or I guess we should do it with the one we have. You could take this expression for d, plug it back into the original, and you should get a statement that says d, or that f equals f. You should get the same thing on both sides of the equation. Okay, so back to our question. D, what applied force would result in a displacement of 1.200 meters? You might be tempted, since we just found the inverse function, to set 1.2 in there and do some extra work in terms of solving for, we could set 1.2 over here and go back through and solve for f, but that would be extra work since we already have a function that is solved in terms of f given a value of d. So what we're really needing to find is just what is f of, or if we have a displacement of 1.200 meters. So f would equal 5 times 1.2. So we just plug in a value of 1.2, we multiply that together, we get 6 plus a half. And so we get 6.50 meters. And I used the value of 3 significant figures because this was a mixed operation of multiplication, time, and addition. Some classes might have you go all the way out to the hundredths place, since you were able to go to hundredths place in both scenarios there. Okay, so to sketch a meaningful plot of d of f, so make sure we're getting the right thing. What's displacement as a function of force? So that means displacement is going to be on the y-axis. We measure that in meters. Force is going to be on the x-axis. We measure that in newtons. We've got a couple points that we know. We know that it goes through 1 and 0.1. We also know that at 5 it goes through 0.9. But one of the main things we know now from having worked it out, we know that its intercept is at negative 0.1. And we know that this slope is 0.2. So those are all important things that we can label on the graph. I've drawn this one mostly to scale, plus or minus a little bit, just because of my inability to draw. But remember, for a meaningful sketch, it doesn't have to be completely drawn to scale. We just have to have enough information to label what's going on. Other things about this we could note are that the end behavior, notice we assume that it keeps going on, that we can continue to apply force and stretch this out further and further. Of course, at some point the spring straightens out and won't go any further, but we have no indication that that arises without more information in the problem, so we would assume that keeps going. We assume that we cannot go past that we cannot have a negative force that we would apply. So we assume that at most we can apply zero force, and so we start here with zero force, and it's displaced by a negative 0.1 from our meter from our measuring point. But we will stop there. We would not continue in the negative direction. It might be that we could, if we're allowed to apply negative forces, we can push it. But again, that's one where we would more likely assume that there would be a limit. And here I've drawn the inverse function. Should have done this in blue, as I've done, to indicate that this is not required for the problem, but just extra information. But this is f as a function of d, which is what we were given originally. So key points of this sketch, and if I had drawn it more to scale, you might see the difference in what flipping over the slope means. But other points that you'll notice the intercept change. So on this one, the x-intercept is at 0.5. So if we're on here, the y-intercept is at 0.5. Similarly, on here, the y-intercept is at negative 1 meter. So here, the x-intercept is at negative 0.1 meter. You'll notice those similarities as you do inverses. And then again, the idea that the slopes are reciprocals of each other. This one is 0.2 or 1/5 because this one has a slope of 5. Again, because of the scaling, you don't really see that, but all good things we can learn about inverses.